getting into reviewing CIP systems, lots of information is available, and we really start to look at when we're out at the plants is around the system configuration and the products. So we really like to look at the system type. You know, what are we looking at? We look at the products. You know, what's it made of? How long does it run? What's the conditions in which they operate? And as well as the production run. As you all know, when we visit, some of the very first things we look at is production records and CIP records. Very, very important. Those are the things that we go by. And if applicable, we also, of course, review microdata to ensure our CIP programs are performing as they should. And then, most important of all, we also perform system audits. Now, Glenn, over the years, has developed this great form that is very, very detailed that goes into everything from the system setup and configuration to the CIP cleaning procedures, as well as flush data, very, very comprehensive form. It also incorporates the types of elements that are on the unit and the sizing, which really helps us understand kind of where the system is today. So if we do have problems in the future, there's always a good point of reference. Another part that, of course, that the membrane team gets into is optimization. Lots of our customers want to be able to save some water, save some chemistry. We all want to be able to do that. And of course, help around with turnaround time. Very invaluable. Another part of our membrane program is troubleshooting. So be able to understand how a system performs and runs, what our membrane program, we must understand the history. Be able to have good history, we need to be able to track some elements and be able to ensure that we're tracking membrane performance, the membrane life, very important. Hey, are these membranes relatively new? Are these old? Have they been around for a long period of time? The membrane program, really like to review what type of program do we have out there? Is it an all enzyme program? Are we using heavy oxidizers? Or is it an NPE free program? Those are all very important factors that go into cleaning programs. Of course, talked about processing and records, and we'll get into that. And a good telltale sign of a system performance is the water flux readings, and of course, our pH meter and pH meter calibration. Again, that's the tool that we use for lots of decision making to ensure that we're maintaining and taking care of those instruments properly. In order to have a good cleaning program, you need to be able to have these valuable items. So a good cleaning program ensures that we have suitable water of quality and of quantity. You've probably been to lots of facilities where if the water quality isn't there, especially around the silica side, we'll get into that a little bit later, can impact the way the system cleans as well as the quantity. So if you have systems that don't have enough water supply and you're especially doing rinses, you're stopping and starting, and that can impact number 2 on the line, which is, of course, rinse times. We discussed that earlier, very, very important to a CIP program. Of course, the correct amount of detergents, that's where we come in as account managers and reps of Hydrite, ensuring that we're hitting the proper targets for pH, temperature, parts per million, having the flows. That's probably the area that we probably struggle with the most, is understanding the flows and pressures. Again, one of the key elements of a CIP system. Getting back, the good program will ensure that we restore the system from a clean water flux, and we'll get into that later on. And a good cleaning program has to be able to handle some process variability, as we all seen does happen in real world. Managing the membrane and membrane life. This is typically handled by the plant, something that they do on a regular basis. but you should just be aware of that it's happening, that they're tracking the element history, serial numbers, the location within the system, and the dates in which they were installed. And for you as a account manager, you'll be able to have access to this document when you need it. It will be used, especially with state inspections. Typically, they'll look at this map here, and here's a good example of one. Up here, you'll see that they talk about, I think this is loop 0A, so typical for a system that's been expanded over time. So that's the loop number, and this one happens to have 6 vessels, and each vessel appears to have about 5 elements. So you can see each location, depending upon where they sit, they'll put down the serial number, also log the manufacturer, what the expected warranty life of that element is. Typically it's 12 months, some last a little longer, some not so much. A lot is going to depend on how the machine runs and how it cleans and level of harshness, if you will. And of course the installation date. Hey, when was this thing put in?
One other thing I'd like to see in that would be the membrane model number or the spacer size as well. So if you run into membrane loading maps that don't have that information, it might be a good idea to talk to your customer about adding that, or at least having a separate document that marks that out as well.
And not all RO elements are the same. They all have different spacer sizes, and UFs have different molecular weights, so you can have lots of variation there. So having that data available, the model number typically will tell you that as well, but you've got to do a little bit of work to find it. But having that information is very, very helpful. Performance, again, something that at the plant level, you may not necessarily be aware or be involved in all of this, but I'm sure when this starts to go awry, this is when they start calling you and looking for help. Some of the things that at the plant level they'll be looking for in measuring membrane system performance is really looking at for leakers. They'll look at the level of protein. They'll maybe be looking at color and turbidity. They'll be looking at conductivity. Some of them measure BOD or COD. Lots of them measure clean water flux. After CIP, that's an indicator that they may come to you and say, hey, I notice our flux isn't where it used to be. Operating pressures, those are the things they'll be looking at as well. Hey, how does the machine run, and is it pressuring out sooner than it used to? Those kinds of things are what they'll look at on a regular basis and may notify you that you have an issue. Product testing, again, this isn't something necessarily that you do, but this is what at the plant level they'll be involved in. And for you is just to understand, these are some of the metrics or some of the things they'll be looking at. Of course, when operating our RO, we'll be measuring solids, typically the refractometer. They'll also be measuring conductivity of the permeate, just to see if they've got leakers. You walking by as an operator or as a account manager, walking by these pieces of equipment, do some visual inspections of the permeate, see if you've got some discolorations or leakers. And they'll all be checking protein levels. There are various instrumentations out there. Most of them are using IR or an FT type system, as well as measuring fat and protein in WPC or WPI, those kinds of things. In measuring those product critical targets, here's give you an idea of how they operate the machines. This happens to be targets for, looks like WPC 34 and WPC 80, and they'll have ranges, much like our chemistry have ranges. Product being sold on the market does have ranges, and there are legal limits to those ranges. So you can see here for WPC 34, minimum requirement is 33.5% protein. So if it's got 33.5% protein, that means it's being made up. The rest of it is being made up with other constituents. You see about 48 to 55% lactose, and we have a little bit of fat, some ash and mineral in there. And believe it or not, there's a little bit of moisture somewhere around that, typically around that 3 to 5%. moisture level. And you can see the ranges for WPC80 and WPI and MPC, and all those will also have their own specific targets. Again, that's what these machines do out there, is essentially generate a product, give you an idea of kind of what the plants are looking at or trying to do with that equipment. As they're measuring and doing all these checks, of course, hopefully they're logging all this information down on process log sheets. Again, good log sheets would have information like feed flow, concentrate flow, solids, in, out. Some of them measure pH, baseline, of course, baseline pressures, stage pressures. Some are looking at turbidity and color, measuring conductivity. Of course, temperature is very important. And there's also maybe some other process changes impacted that may be logged. CIP. So we talked a little bit about product logs. There's also CIP logs. We heavily rely on these logs. And what's on there, should be things like the water pH of the water supply. It's good to understand the baseline, where we're starting from. Feed rates, you'll have feed flow across the feed side, permeate rates. Also, there's a concentrate meter. Lots of these systems will also, in order to get enough cross flow across that baseline, they'll have bypasses around that concentrate flow meter and valve. So that reading may be not representative of the total flow. Baseline pressures, temperatures, of course, and the step times, of course, the amounts of chemistry being used, including all the boosts and the pH. You all know beginning, middle, and end. Very, very important to understand what that is, both on pH and our ppm, and especially understanding where we are with our chlorine concentrations at the very end of our CIP, and of course, water flux.
That brings us to system flux. Of course, just on a couple notes about flux, first of all. Most of us understand that we run a flux test on a system to determine the cleanliness or the state of the membranes, if we brought them back to the state they were before production started that day. So we bring them back to the state they were clean the previous day, and on and on and on. The term flux is kind of a loose term. Most of us, when we talk about flux, we're actually talking about the permeate rate out of each stage or loop of a membrane system in gallons per minute. And you'll see on the left-hand side those analog or those rotometer gauges. And if you're lucky enough to have a more modern system, or people that spend a little more money, you'll have electronic flow meters, which are always great because those don't have any variability, and you can read a more accurate reading, in my opinion. But what I was saying about flux isn't exactly the rate of permeate flow. Okay, we call it that, but to be a true flux, you have to look at your permeate flow rate and also take into consideration the membrane area that permeate is flowing through. So the flux, in actuality, technically the flux is the permeate flow rate per membrane area. So you get your gallon per minute permeate flow divided by your membrane area per unit of time. Okay, so basically it's measured in liters per square meter per hour. Typically, when you see flux on a log sheet, it just means the gallons per minute of permeate. But why is flux important? If you want to compare different stages or loops of a membrane system, different stages could have different membrane spacer sizes, and they could have different membrane area. So if you want to get an idea how one bank or loop of membranes is performing against another to see if maybe one is cleaner or dirtier than another, you could use the actual flux reading that compensates for the variance in area between two different membrane loops or stages. Little technical term, but hey, let's raise the bar and get a little more education into you. So the clean water flux, as I alluded to, basically is a way to measure the performance of the membranes and the effectiveness of a cleaning program. Simply because we can't take a membrane out of its vessel, cut it open, unroll it, and look for cleanliness, roll it back up and put it back in. So we need a non-destructive way of testing whether or not our cleaning program is effective or not. And flux The flux results can be a direct, it can be directly correlated to an effective cleaning program, but there's a number of other things that I'll talk about that can affect your flux readings, and we'll get into that in a minute. But basically, like I said before, typically what we're doing when we do a clean water flux test and we're logging the data, we're going to compare the same loop to itself on different days. If you want to get a true comparison of flux, then you would take in consideration membrane area, and then you could compare different loops to each other. Anyway, if that makes sense. But basically, the bottom line, it's taken after full CIP to establish if the system has been cleaned sufficiently and restored to its original state. So the key points for an effective clean water flux, okay? And I'm going to start this by kind of giving a little background information. A lot of membrane manufacturers, membrane system manufacturers, will program their own way of measuring clean water flux. Some of them will run the system as if in production mode with the feed pumps and the loop pumps circulating and cycling. Like, for instance, an RO system or a nano may flux all loops concurrently. A UF or an MF system may do individual loops one at a time because they can isolate the loops and do that. But in all cases, what they're doing is they're bringing the system to a consistent pressure and potentially a consistent temperature, because flux can vary greatly based on varying pressures and temperatures that the membranes are subjected to. So typically, a typical flux program will bring the system to a set pressure and temperature, and if it cannot bring it to a set temperature, there are mathematical conversions or correction factors that the membrane OEM can install to compensate for differences in temperature, because sometimes people's water temperature will vary depending on the source of that water. It could be cow water from a silo that may be 100 degrees, and if they run out, they may do a flux test with city water that could be as low as 50 degrees, and that can greatly affect your flux ratings. But the keys to having an effective clean water flux are constant flow, so to make sure the balance tanks have enough solution so the pumps don't run dry or run out of supply and start to cavitate. And then maintain constant and consistent temperature. And by the constant temperature means we don't want the temperature to raise significantly as we go fluxing from one loop to the next performing the test. And then consistent temperature that is done at the same temperature potentially day after day. And then we want to log those key parameters along with that data and put it into a log sheet so we can compare. And we can compare and review that to previous readings. A lot of people will have a data historian, or other people will have the paper sheets. Other points to note: it's beneficial for as an account manager to make sure that if a customer is going to be changing out membranes, it's a good idea if you can, after a couple of days of production, get in there and get the flux readings for those new membranes to establish a clean baseline, because that's assuming that they're going to run this thing for a day or two and they're not going to follow out the membranes, okay? That way, if something happens as time goes on, we can compare what the new membranes fluxed versus ones that have been in the system a while. So it's a good idea. And one point that I want to note is that when membranes are just changed out with new ones, it's not uncommon for you to get a really high flux reading at the beginning, and for after it's been after that those membranes have been in service for a couple of days, for it to lose about 10% of its capacity, but it should level off. And Carl had pointed out that sometimes the membranes can start out with a lower flux, and then they can actually gain flux readings or gain permeation rate, and then they eventually settle out from that. But the key is, after they have been in service for 2-3 days, they should, after a proper cleaning program, return to the same level day after day. And we'll see what a graph of that looks like. Now, the reason that we can have variances in flux is that there's always systems out there where nobody has, it's generally very rare to find one complete membrane system that'll have all of the same manufacturer membranes in it. Those membrane manufacturer reps are constantly out there trying to promote their latest and greatest products, and they're always getting customers to try a loop or two or a couple vessels of their membrane to see if it has better performance over their competition. So it's not uncommon for customers to have a mixture of membranes in their system. That probably would all be, of course, be UF membranes or RO membranes. They'd all be the same type of membrane, but they could have different manufacturers that tout different benefits. So membrane, when you do a flux test, we could have flux differences based on different membrane manufacturers, different age of membranes, or different molecular weight cutoffs in the case of perhaps UF membranes. And those will all produce different clean water flux values. So like I said, it's not uncommon to see major flux variations between loops in different loops in the same system due to those potential differences. And that's why it's always very important to have a current and accurate membrane loading map, or at least know who keeps that data and become their friend, so they're willing to share it with you.
One other area to keep in mind is oftentimes you'll see out on the floor, especially with ROs, where they'll put in a bank or so with NF elements. And then you'll see that one really flux considerably higher than the other ones. You're probably wondering what's going on here, and that's what you may find.
The reason for that, especially with an RO, as you concentrate material, your osmotic pressure goes way up. So it's not uncommon for the latter stages of a RO system to have nanomembranes, because they essentially will flux with lower pressures. And why is that important? Because it's much less energy consumption for the system to not have to get up to 600 psi to squeeze that last bit of water out. The clean water flux tracking, of course, this is an example of somebody that has used an Excel spreadsheet. And I would encourage account managers to, at least on a weekly basis or as often as they can, look at the flux trends on a system. Because even though a system may get through production on a day-to-day basis, it could slowly lose capacity, almost an imperceptible amount every day, till it gets to a point where all of a sudden there's a problem. And if you pull these flux readings, you could see that the issue maybe occurred a couple weeks ago, and now it's finally causing problems with the plant. The sooner you can jump on a problem where fluxes are trending downward, the easier it is to correct. So I strongly encourage people to look at the clean water flux trends or this data. A lot of customers today will enter this data and actually have be put into trend line sheets that are much easier to look at. So I encourage people to do that, and that way they can identify problems and correct them before they become a real issue where the plant is going to be faced with a potential shutdown to take their system offline, so we can clean it for 3 days to bring it back to normal. If the system, the programmer that made the system does not have mathematical factors or temperature or pressure correction factors, and if those two parameters during the flux test can vary from a day-to-day basis, generally you won't see the pressures vary unless we're having a pump issue. But generally, if your water temperature can vary from a day-to-day basis, you could see, if you trend flux readings, you could see something like this happening, where, oh my gosh, it looks like it's all over the place. Looks like some days got good cleaning, other days it was bad. And that's because that could be due to the parameter variations of temperature. So this can be corrected, and on one of the next slides, we might have a normalized flux reading. So in order to make sense of a flux reading, we need to correct or normalize those flux readings. So typically on an RO system, the membranes are designed to be flux tested at a standard temperature of 77 degrees and 100 psi. Now that's industry standard for RO membranes, but our UF and MF membranes tend to flux a lot more than ROs, so they may have a lower baseline pressure, and it may just be that the system is set to flux at a different temperature, because as we all know, let's say if we tried to achieve the same temperature day after day, the water temperature at the plant can vary, and a lot of times they don't want to wait for it to raise from 60 degrees up to 77 degrees, or if it's too hot, to cool it down. So as long as it's a standard temperature, and if it's not, they use a correction factor to account for that temperature change. That can be programmed in. And the next slide will show normalized, the same data you saw in the last slide. Here it is again running through the normalization program with the temperature correction factors. So you can see that at the beginning of this month-long area of sampling of flux readings, that all of a sudden there was a spike in flux somewhere at the third or fourth day. There could have been a membrane change out at that time, and then as it moves on, you see that it normalized, and we had a long series of plateaus. Pay no attention to the fact that we're missing a bunch of data about 2/3 of the way of this through this graph. It just wants to illustrate that you do get these flux readings. You will have some normal day-to-day fluctuation, but for the most part, you should establish a upper and lower control limit average that system should return to. And then you can see somewhere towards the end of this graph where we took a dip, and then it slowly recovered, that could have been an upset during the day. We could have had a pasteurizer divert. We could have had a fine saver screen, get a bunch of cheese fines in the system, or a separator malfunction and release a bunch of fat to the system. And what could have caused some lower fluxes, and then you can see that it slowly recovered. But anyway, that's what a normalized flux graph looks like. And that way we can compare to see how the system is, what the health of the system is. And this one looks pretty good. And so the causes of low water flux, okay, they can be a number, but there can be a number of different reasons, but I break it up into a couple of different main categories. One is the system isn't coming clean. The other one is the membranes could have been damaged due to high operating pressures or being over temperature. So the issues of not coming clean could be the cleaning programs not being followed correctly. So we need to check for chemical concentrations. Do they get in the right pHs during the wash? Is the surfactant pump working? There's no greater way to mess up a membrane system is if they don't get the proper amounts of surfactants during the washes. And, you know, since we're not titrating or checking pH that tells us surfactant levels, sometimes, you know, what can happen, as I've seen, is a surfactant pump can fail, and we don't get the right amount of surfactant, or we don't get any at all. And the system can actually run a day or two without that before it totally crashes. So keep that in mind. So the remedy to that is to review the cleaning program and check everything and make sure the pumps are working, make sure that the levels in the drums are dropping as you would expect from what the surveyed chemical usage amount is, okay? The other reason a system could be dirty is they have a feed stream upset. The feed stream quality all of a sudden takes a dive, or they get a process stream from a different supplier. They could have denatured protein. All kinds of things can happen. They could have extraneous material or something that they're not expecting in their feed stream. Or if they changed water supplies, they went from cow water to well water, and the well water could have some type of foulant in it, okay? All these things can happen, and they all are the cause of poorly cleaned or membranes that are still dirty. The other thing that can happen is mechanical damage to membranes that can cause low water flux. And the problem with that is if they overpressurize membranes, if the operators push them too hard and get the baseline pressures too high, you can crush or collapse the membranes, and you can restrict those permeate flow channels that you remember seeing from the scanning electron microscope. And once you do that, once you physically damage a membrane due to overpressurization or getting them too hot, there's no bringing them back. Low water fluxes can also be caused by system hydraulics. If we have a failing pump or a failing sensor in the system where you think you're getting the right pressure and the right temperature in fluxing, but it's actually wrong, that can cause differences as well. So therefore, it's also useful sometimes to compare electronic gauges or digital gauges with analog counterparts if they have both on the system. Or chemistry change. That's why it's important. If we ever make a change to a cleaning program, we don't want to make too many changes at once, and we want to monitor that change, because sometimes it can take 2-3 weeks or longer for a small chemistry change for the effects of that to show up. The system, knock on wood, could get better than it was, or it could get worse, but it may be slowly, incrementally better or worse as days go on. So we have to make sure we look at that as well. If you are having a system problem determining why we're getting low water fluxes, and you look at all these things and you're not sure, give us a call. That's what we're here to help support you with, okay? Be alert for changes in the operation and the quality of the feed stream. That's tantamount to what you need to do to make sure the system runs the same day after day. Review production log sheets. You know, is the membrane plant performing as designed? Okay. Again, it's just the same checklist. Make sure the cleaning program is being verified. And we all know now a little bit more from this training how to check the proper flows and pressures, right? How do you know if you have the proper flow across the membrane? You do your little calculation where you subtract your baseline pressure from your loop pressure and divide by the number of membranes in each vessel. And as a rule of thumb goes, you should be between 10 to 15 psi. Slight variations depending on membrane spacer size and different type of membrane, but that's you get the point, okay? Water temperature, are you getting the proper temperature for cleaning? Is it not too hot? Is it not too cold? Is it just right, okay? And then the water pH, different water supplies can have different contaminants in them. Are they using a good, fresh, good quality, low micro cow water to clean? Well, that will give you your best cleaning results. Did they have to switch to well water that maybe have some contamination and a lot of hardness to it? That can cause problems as well. And then, of course, finally, excessive foam in your balance tanks. granted, we are using products that tend to foam a lot to clean the membranes, but if the system is designed properly with anti-foam elbows or returns back to the feed tank or to the balance tank below the solution level, foam should be kept to a minimum. If you start to see a whole bunch of foam coming out of those balance tanks during CIP, that could be an indication that you have leaky pump seals, that they're sucking air into the solution and training it and causing excessive foam, which is also going to greatly compromise your cleaning and lead to low water flux readings.
Troubleshooting. We're going to touch on this a little bit. I think the next couple of slides are generally involving troubleshooting that is linked to fouling, so a cleaning issue. Either the program is unsuitable or often it's not being followed properly. And this is kind of a methodology for figuring out what the culprit is and the methods that we're going to utilize in order to resolve it. So the first foulant that we're going to examine is fat. Now this is going to be an issue in your feed streams that involve fatty feed, so your milk. This is going to be possibly something going on in your MFs with your wheys, trying to get rid of that procream. But we're going to find it basically by a system analysis that's going to show increased baseline pressures over time or more rapidly increasing baseline pressures. And kind of the gold standard for a lot of these analysis is going to be visual inspection of the membrane and the soil that we're actually getting off of it. So if this is not a system that generally handles high fat and it gets fat from an upstream source like a separator, this can be a common issue on RO units that are not supposed to be seeing fat but suddenly get swamped with some from upstream. Correcting it is going to be a matter of targeting the fact that we're dealing with fat and using the correct chemistry and cleaning techniques to restore the system. For general purposes, this is going to mean using the highest possible temperatures without compromising the membrane. So this is going to have to do with liquefying the fat and making it so that it moves better, doesn't get all stucky and gummy in one place. And that applies both to the washes and to the rinses. The amount of surfactant that we use is probably going to go up, but that also means from a product standpoint that to make sure that we don't end up with surfactant left over during production, we want to make sure to increase the rinses. Another tool that is in our bag for fat is Ultrasolve. And this is kind of a solvent that is going to help the emulsification, especially of fats. And we can use this at 0.1 to 0.2 fluid ounces per gallon. But just remember back to some of our previous chemistry slides, this used at a regular basis can result in membrane damage. So we're mainly using this in a remedial capacity membranes that we know are fouled with fat. And finally, that can sort of be incompatible with chlorine usage, which it can be some sort of concerns about whether or not taking out the chlorine is going to lead to more fouling. But if we're strictly dealing with fat, chlorine is not going to do much to remove that fat. So if a remedial wash, we want to go ahead and have more washes that are targeted with surfactants and the Ultrasolve, we can see a significant increase in the cleaning of those membranes. And if it is a fat issue, they're going to be returned to capacity pretty quickly. The next foulant we're going to look at is protein. Again, this is going to have similar symptoms from a hydraulics perspective as far as the increase in baseline pressure. And the other thing that can sort of clue us in is if they've sort of been playing with ratio controls and trying to come up with a more concentrated protein product. A lot of times systems might get pushed beyond their normal uses, and our programs for washing have not been adjusted accordingly. So you can end up with protein that just starts to accumulate because of a change in production parameters without a change in the wash procedure. Again, this is also going to be identified most easily from a visual inspection. So this is going to be your autopsy, pulling a membrane out and actually looking at what's on the surface. But the ultimate resolution is going to be, again, targeting that specific soil. This is going to be more common on your protein systems, but it can be on RO systems that, again, aren't supposed to be seeing that product that is high in protein because of a leak upstream. So I've seen this on ROs. I've even seen it on polishers that weren't really supposed to be seeing protein at all, but the RO upstream of them was leaking. So even though we can come up with a chemical solution to clean these membranes, a long-term fix is going to require that we make sure to correct the issue, which in a lot of cases for systems that aren't supposed to see protein means finding the leak upstream. Another thing that can cause protein to become more of a problem is if it is denatured, and this can be a result of pH or entrained air cavitation, causing them to become under basically the perfect storm of conditions, a very sticky, gummy complex with lactic acid that might also be in the feed stream. In either way, targeting the protein soil is going to be the best way to remove this. Pictures below kind of demonstrate a methodology for figuring out that we are dealing with protein soil. This is using a couple of different solutions to find out what dissolves it best. And this really is going to be the most practical way to do a soil analysis. I know we have a whole bunch of fancy tools that I'll get into at the end in our lab, and it's great to be able to figure out precisely what you're dealing with. But for the purposes of time and really, like I said, just practically doing an analysis that includes the solution, doing a soil analysis, in this case, this is just basically pulling out the feed spacer of a membrane that's got obviously entrapped soil and dunking it into different types of solutions. We're both going to figure out that we're dealing, in this case, with protein and know exactly what we need to resolve it. So our rinses are going to be really vital in general for a wash, but in resolving a protein issue, we want to get as much of that loose protein off as possible and leave only soil that's actually an issue on the membrane for our chemistry to deal with. For an enzyme solution, which is going to be a really great way to treat a protein problem, we're going to increase the strength and we're going to drop the pH. Now, I know Glenn talked a little bit in the last presentation on chemistry about the optimal range for our enzyme products, but realize that that optimal range is targeting both the optimal range for the enzyme and the surfactant and other builders. If we're particularly targeting the maximal activity of our enzyme in our products, we want to hit that lower end of the pH scale. So that 9 to 9.5, and we want to continue checking that, especially if we don't have a built alkaline product in the system to maintain that pH. The pH dropping is actually an indication that it is working, because if you remember, proteins are constituent, they're made up of amino acids, and so when those get broken off, it's going to reduce the pH of your solution unless you have a built caustic in the solution. Also, there could be potential problems if the pH gets too high, so this is not something you want to just, hey, we need a remedial wash, let's jack up the pH and throw the enzyme in. For really optimal effects, you want to target that low range and increase the enzyme concentration.
So just keep in mind there, as you see, especially the center picture there, you can see if your caustic level pH gets too high, you can actually make that gelling worse. You can start to really gel up inside those elements. Just makes it hard to get out of there. It's one of the reasons to keep that pH maybe a little on the lower side if you have that heavy protein fouling in there, because high pH can, of course, make it much more difficult.
And as far as if you're on a system that generally doesn't run enzyme, or there's a focus on using chlorine, that is a method for breaking up the protein. Again, you're not going to want to go too high on your causticity, but maintaining those chlorine levels is going to be important. And if you can't maintain them and you've increased the amount of chlorine in the system by boosting it to an amount that totals twice the amount of the original dose, go ahead and dump that solution to the floor and start over, because what you're probably dealing with is protein that's been removed from the membrane surface, but is still circulating in solution and eating up that chlorine. And that's not the target we want to go after. And so, the only way to get after the foulant that's actually on the membrane is to dump the dirty solution so we can get something in there that's actually attacking the problem. ROs and NFs don't have the luxury of the oxidizer protein removal. In most cases, we're pretty much not going to want to touch them with anything that's oxidizing, but there's probably should be an enzyme wash if there's any protein product involved in general. If there's not, we can go ahead and add one as a remedial step, or maybe even for a longer term period. And if there's only like a weekly enzyme wash, we can increase that to daily. And just remember, the real advantage behind enzymes is we aren't going to be putting any additional chemical stress on these membranes. The enzyme is going to only specifically target proteins and use all of its force against them. So the oxidizers that can be used on MFs and UFs, it might be cheap chemistry, but it's sort of a shotgun blast, see what it hits type of chemistry, whereas the enzyme for both of them is going to be a very targeted approach. In both cases, just referring back to the ultimate solution to this, if this system is going to need a wash that's going to improve upon its proteolytic activity because they've changed the process, that's one thing. But if this system is not supposed to have seen a lot of protein, and it suddenly is, chances are we need to look upstream for the problem for a long-term solution. Your leaking lip seals, your old, I've seen plants that run UF membranes for like nearly 5 years, and not only are they losing money down the drain in product, but you are putting additional stress and reducing the capacity of the downstream membranes. Just a small note at the bottom here, the chlorine in an MF system might be stable and still have a protein issue. And this kind of has to do with the fact that, if you'll remember, membranes wash at low pressures. So the goal is maximum flow, not maximum permeation. So it's kind of been shown that replacing one of those chlorinated alkaline steps with an enzyme step can be a successful solution to a fouled MF system that is seeing a lot of protein foulant. Mineral can be another foulant. This is going to be especially typical on RO and NF membranes. And the typical additional factor that's going to indicate you're dealing with mineral as a foulant is that it's often going to show up on the last stages. So remember, this is where the product is going to be maximally concentrated. Probably it's going to have seen the most amount of excess heat off of pumps. And it's kind of a recipe for the fallout of mineral foulants. So causes: running very hot, trying to achieve too high of solids, or trying to do so without adjusting the pH in order to hold those minerals in solution. Ironically, another cause can be CIP. If we're using improper water that's really high in mineral, that can actually cause a collection of mineral over time that fouls the membranes out. So the resolutions are, hey, let's try to get this process as cool as possible. Let's adjust that feed stream. A lot of times we're dealing with salts of calcium phosphate, especially with dairy products, and targeting that 5.8, 5.9 pH for the product is going to reduce the probability that that calcium drops out. For CIP, we're going to start with acid wash, so sort of change things over perhaps. If they've got an alkaline first, maybe change that so that we can start hitting the mineral as soon as possible, and repeat it if we're rising in pH too much and seeing that the acid is basically getting consumed by reacting with the mineral foulant. Another method, if an acid wash is not enough or is not practical for the situation, is to add descale. And this might be a more long-term solution, but we do have methods for checking what a proper dose is, both for a recovery wash and for a long-term solution to a mineral problem that is occurring on an RO or an NF system.
I just wanted to mention one thing. As you stated before, the normal dairy soils that we'll expect will be phosphate and calcium scales, phosphates or carbonates that are readily soluble in acid normally. So where the EDTA comes in is if you, one of two things. If you have mineral soils, perhaps from a poor quality water supply, or something unexpected that isn't soluble at the regular acid pHs, that's where the EDTA comes in. So the EDTA may not necessarily, the descale may not necessarily chelate just calcium. It may be other salts like calcium sulfate or other types of mineral salts that aren't soluble. And the other thing is the descale would come in is if you want to attempt eliminating an acid wash on a daily basis by trying to do two things with the alkaline wash, get out the organic plus the mineral at the same time. And then in that case, you could add descale to an alkaline wash to get that done.
So the last category of actual fouling that we're going to cover is a microbiological fouling. So there's a lot of terminology that's thrown around in the industry as far as like biofilms and different types of biological matrix, but when it comes down to it, micro does actually present a little bit of its own issue. So it's caused usually by inadequate CIP or if there's a problem with actually the feed stream being contaminated. Remember, a lot of times, especially on the concentrate side of membranes, we're going to just be increasing the problem if it's a micro issue. There's inadequate system hydraulics. If we're not basically just getting enough turbulence in the system, this can be an issue. And also, this can come completely outside the product, simply from the CIP water. This is also a problem if there's just not a sanitized step that's happening regularly. This can occur. And kind of the big issue with micro is that it's not just some individual soil. It sort of complexes itself, and it becomes a compounding issue that kind of takes and deposits a lot of foulant right on the membrane and causes issues over time. Finding this issue as quickly as possible is going to be very important. And a lot of times it's actually going to come to attention because they're going to see higher counts in their product. And that'll start setting off some alarm bells. Obviously, we need to isolate it to make sure that it's at the membrane system source. But in the meantime, you can even just start doing your full CIP audit. You can start checking the feed stream and concentrate samples, so comparing what it comes in as and what it goes out as to see if you have micro that's growing in the system. And the other thing to check is the CIP water, and not just the silo, but the distribution line. So often there can be a problem where you got a clean silo and you got a clean system, but I've heard it that people might forget to CIP the distribution lines, and then you're just sending clean water through a dirty line that's putting dirt in a system, and that can sort of fly under the radar for a while. It seems obvious, but a lot of solving things is at its base a very simple issue that just got overlooked. We can totally hit them chemically with a hot bisulfite wash. This is going to be utilizing our Hydrosoak 180 and membrane additive 531, and you're going to go ahead and put those in the system, and that'll help to eliminate a lot of the micro, much like a sanitized step. But we're going to do this in addition to the sanitized step. So completing a daily sanitize. There's also hot water sanitize. And the other thing to add is this can come up a lot of times if there are membranes that are just sitting in water, if they've got a lot of downtime and they're not using that soak. So our soak products like the Hydrosoak 180, that's really where they shine, is they're going to be in those systems when they're down, and they're going to inhibit growth. So they're not really in themselves going to be as aggressive as a sanitize, but that's also kind of the point as far as membrane preservation. But they are going to basically keep it bacteriostatic. So if there is any micro in the system that somehow survives them, it's really not going to have a good chance at growing. One more thing that I just want to add on this issue, if the counts go up on a product, but you're not seeing actual fouling symptoms, so you're not seeing the decline in flux or the increase in baseline pressure, make sure that your customer is sampling correctly. So I remember distinctly a case where I went into a place and they thought they had a significant micro issue. They were getting ready to swap out all of their membranes, and one of the recommendations that we gave them was just clean out your sample ports. And funny, their micro issue completely disappeared as soon as they cleaned out their sample ports. So just remember that where they're getting their information from, in this case, the spigots and the samples, there are really good best practices on how to take those samples, and I wouldn't want to necessarily step in any plant's way of how they're doing things, but it might be worth just understanding what they're doing and then taking a look at that source to figure out if they're actually getting a clean sample. because you can think that you have a significant problem, and if it's not actually showing up in the hydraulics of the system, which you're sort of setting out to fix, it might not be the problem that you think it is.
If anybody has any need or desire to try the special hot acid wash using hydrosilk and membrane additive 531, just be aware membrane additive 531 acts as a very strong buffer, and it may take extra acid or boosting with plant acid to attain the desired pH that you want between 3.5 and 3.8. It will cause additional acid usage, and that's a normal thing. Just be aware of that, because what's happening is the membrane additive 531, as you acidify it, it releases SO2, and SO2 is what we're wanting to release to get and go after the bacteria, yeasts, and other such species in the system that we're trying to attack.
All right, so the last thing is going to be hydrophobic membranes I'm going to talk about. And basically what we're discussing here is when you have all the symptoms of a foulant and none of the actual signs when you cut open a membrane. So if you're not finding soil, if you've sent something into the lab and it's not showing that there's any foulant in the membranes, it's often going to be because the membranes themselves, which are made out of a hydrophobic polymer, are just not permeating properly. You're going to see this in a case example with new membranes that haven't received an alkaline wash, haven't seen any surfactant, or are not getting enough surfactant, and sometimes in higher fat applications where that surfactant that does get put into the wash is being completely consumed or completely emulsifying the soil, and there's not enough residual. There does need to be a little bit of residual surfactant on the membranes for them to have their best function. And in order to restore this, we're going to do something in addition to the normal CIP. So you're going to run that full CIP and complete an additional surfactant wash. And we're going to bump up the surfactant usage to 3 times its use rate, which also means we do need to get the excess out of the system before production. So we're going to double the rinse afterwards. There is a copy of the rewriting procedure on the Hydrite Membrane Assistant if you have access to that. If you don't, talk to me, and I can make sure that we can get you access to those resources. Checking the clean water flux is going to be sort of the standard for determining whether or not the membrane is re-wet, but you're also going to be able to see this in restored production once the surfactant is on there. So here's just kind of the use rates for the bright cleanse or the HydroCleanse, and we're going to definitely be targeting those higher end use rates for fat applications.
You know, there's lots of great information on these slides, and we covered lots of different tools and techniques that we use to, you know, solve issues, recover membranes, and try to get systems restored back to their, you know, standard cleaning and operating performance. Please get the membrane team involved when you're doing these things. Don't go out and try them on your own. You know, like those things always say, don't try this at home, if you will, right? Get help. That's what we're here for. We'll walk you through these. Come on site if you need to, but just be aware. Just don't you know, start doing this stuff without getting some help, and get the team involved.
This brings us on to membrane CIP best practices. Basically, I just want a few rules of thumb I wanted to go through here with everybody of standard best practices. Regarding cleaning procedures, okay, there's a few things to note. Always follow the procedure as written. Don't play chemists on your own and substitute chemicals. We realize that on occasion, a customer may inadvertently run out of something, and you can try to find and help them out so that they can continue running by looking for a substitution. Please call one of the membrane team, and we can make recommendations of something else they might have on site. We obviously want to avoid things happening like if you run out of HydroCleanse, we don't want to use a quat-based surfactant in place of it. We can have catastrophic results if that happens. So if you're, you know, need to look at something or to borrow some chemical from somewhere else, we can give you not only suggestions to use, but also some potential suggestions on the differing use rate amounts if need be as well. So we know things happen. but please contact one of us because we want to save you from future headaches or doing something that could be detrimental to membranes. Another thing that's a big pet peeve of mine for people that don't have automated dispense systems, if they are having the operators measure out the chemical by hand and put it into the system, there's a couple of things we should know. Number one, we should have a separate container and drum pump for each chemical being used. You do not want to mix concentrated chemicals. That can be a problem. I was at one facility where they were doing an enzyme wash, and the operator was getting all the chemicals lined up in preparation for that enzyme wash, and he was mixing the concentrated caustic in a 5-gallon pail with the enzyme. Well, what they didn't realize is they were denaturing that enzyme and rendering it useless before they put it into their machine. All right, so we want to make sure we keep concentrated chemicals segregated, do not cross-contaminate. And when you are adding chemicals to a system, the key is to add them slowly. We don't want to have a mass dosing into the feed balance tank or other balance tanks to cause a shock to the membranes. We want to get those chemicals added slowly so they have a chance to disperse and eliminate those very high or low pH shocks, depending on what you're putting in, okay? And then, of course, with the cleaning procedure, make sure as part of your checks, you're verifying that all times, volumes, and temperatures, all the wash parameters are being met for each wash and rinse, okay? That's troubleshooting and just auditing 101. And then also, they have to make sure that the operators and as an account manager, you're verifying that they're taking and logging all of their proper pH and chemical concentration readings during CIP on the proper log sheet. And the thing is if they miss a reading, people get busy, correct? If they miss a reading, they should just leave it blank and put down missed reading rather than trying to guess what the system would be at. And of course, they know that where the range should be. Incorrect data is worse than having no data at all, as long as it's not a recurring issue, okay? And having to do with proper concentrations and chemical amounts, we want to make sure we have properly calibrated and maintained pH meters with a properly maintained log of pH calibration. Fresh buffers should be used. I would recommend a daily basis, but if they change them out without contaminating them on a weekly basis, that's fine, as long as they're only used for pH calibration and don't get contaminated. Test kit reagents for testing sanitizer and chlorine. We want to make sure we have fresh test kit reagents that haven't been left open with the caps off or labels that we can't see on the bottles, that type of thing. Just your general housekeeping stuff. It's also very important to allow enough time for the chemicals to get sufficiently mixed into the system before grabbing your checks for your chemical. And a couple of notes on where do you take your chemicals when you're going to check your system, okay? On UF and MF systems, of course, we know those have very large membrane pores in comparisons to ROs and nanos. You're essentially going to have the same chemistry on both sides of the membrane, either in the permeate stream or in the concentrate stream, provided that the chemicals are sufficiently mixed in. So it doesn't really matter where you take your chemical sample. You could take it from the concentrate line, you could take it out of a permeate sample port, doesn't matter. But an RO and a nano, think about what you've learned about ROs and nanos. What do they pass through their membranes? They pass just water for the most part. That's what they're supposed to if they're in good condition, right? So if you go and take a sample for your pH checks or your chemical titration checks out of the concentrate sample port, which is very common, that is at the end of the system where each of the stages upstream have removed some water. So ideally, you could be getting a sample that you're checking that's going to be more concentrated than the average in the system because you've removed that water. So as my recommendation, if you're checking ROs and nano units, or any unit for that matter, the ideal place to take the sample would be out of the feed balance tank if they have a sample port in that. If they do not have a sample port, then take care, if you're going to get a sample from there, shut off any spray balls that may come on periodically while taking your sample to avoid being sprayed in the face and playing Russian roulette. Check your chlorine levels on your final wash. It's recommended every 5 minutes or as often as you can, and then make additions as the chlorine levels drop below the necessary minimum concentration. It doesn't make sense to monitor your chlorine on a first wash, except that the initial dosing amount doesn't go over the maximum recommended amount of ppms. But if there's a lot of soil in the solution, that chlorine is going to fall off so fast, it doesn't make sense to maintain it. It's kind of a garbage wash, get it in, get it out. is the final wash, that if you do have a final chlorinated alkaline wash on your UF system or MF system, that's where you want to make sure you maintain that level of chlorine. If the chlorine falls off quickly, even after numerous additions, it may indicate that you have still a significant amount of protein or soil in your system. You may need to do an additional wash. Anytime you would chemical, boost the chemical, and then take a resulting pH, make sure that's also logged on your CIP log sheet, because for us, it helps to track, how a system is performing, and also for budgeting and survey purposes. We might have initial dosing amounts, but we also need to take in consideration typically what that unit uses as chemical boosts in order to provide proper survey information. So when you're doing your budgeting and amounts for the year coming on, a lot of your customers, you can take into consideration, because sometimes boost amounts can be significant, especially if you annualize them out.
Very important there as well. It helps us understand the previous steps too. So, if you get to the last step and we're having to boost chlorine quite a bit, that may be an indicator that our enzyme step isn't working right, or something upstream, the previous steps, we may need to modify to help get that system clean.
For instance, if you're finding you're having to use an extra 20 gallons of chlorine on your final wash, what kind of damage is all that oxide doing to those first membranes that are clean before it gets to maybe the rear end membranes that aren't? You could be doing some damage. So it may be beneficial to replace one of those chlorinated alkaline washes with an enzyme wash somewhere in the middle. They'd be much more effective at removing protein. So chlorine is, I don't want to use the word cheap, but it's mainly economical, but it can be very aggressive on membranes, and it can compromise your membrane life very easily. So that's one thing to consider. Final best practices sheet has to do with monitoring not only your chemical data and add that on the log sheet, but also your CIP hydraulic data. So you also, during CIP, want to know your flows, your feed flow, permeate flow of each loop, and your concentrate flow. But keep in mind that a lot of times there might be a bypass valve that bypasses the concentrate flow meter and concentrate valve to get more CIP flow, in which case your concentrate flow would be meaningless, so why mark it down? Also, if possible, if the system has CIP booster pumps and their output is known and potentially their flow rate is known, you might want to mark that down as well. And why would we want to know booster pumps? Well, let's say we're getting compromised cleaning, and because the baseline's not being fed enough to get proper cross flow across your membranes. If we know there's booster pumps in the system and those might not be running at their maximum speed, we may be able to speed up those booster pumps to more efficiently troubleshoot and get the baseline supplied. I know I'm getting a little into the weeds, so I'll move on. But anyway, also pressures, very important to monitor baseline pressures in individual stages and loops. And why is that? So that we can calculate that delta P to determine if we have proper cross flow going across the membranes for efficient cleaning. And anytime there's a pump with an output, if applicable, if you can mark that down as well, that would help us evaluate your system. Then finally, what if? This is the big one. What if during the course of a CIP audit, you find that the wash is outside of the allowable pH range? Okay. A lot of times our procedures will state the fact that if the pH is out of range, immediately flush the system or add fresh water to it to bring the pH in. So I want to just kind of elaborate on that just a touch. If you're there checking your system and the pH is only out by a small amount, less than 2/10 of a pH unit or less, or if your concentration on chlorine is over your maximum of 180 by 20 ppm or less, okay, don't panic. Membranes have a little tolerance built into them. They're not going to be fried if you're a little bit outside of your ranges, okay? So let the wash finish, and then review the operator log sheets or monitor your system again the next night. And if it's continually out on the, outside of the range by a little bit, make the chemical adjustment and then re-verify to make sure it comes into range, okay? You don't have to sweat it and pull your hair out and jump up and down and go hit the E-stop on the system, all right? So that's for if it's outside the range by a small amount, kind of with the guidelines I told you. If you find that something failed, a pump stayed on, or the operator added the wrong amount of chemical, and your system is sitting at pH 12, or it's at 500 ppm chlorine, or the pH is down to 1.2, you want to immediately add fresh water to that system to get the chemical concentration within the range so we don't cause membrane damage. And if you can't, add enough water to that system to get it down, then you want to immediately dump, rinse, and recharge that system with the proper amount of chemicals, okay? Because the extreme ends of the pH will do damage, all right? And if you do have some issues that happens, check your chemical dosing system if you have one, correct any issues, re-educate operators, and anytime a change is made and you make adjustments, you must verify those adjustments got you into the ranges that you want. So hopefully that provides a little more background, a little more nuance to what happens, the what if of being outside the chemical range. The main thing is that, little changes here and there, as long as they're the exception rather than the rule, we still want to address and make sure, but if anything major happens, yeah, you got to get that stuff out of the system. So
troubleshooting, what can cause element damage? So again, what can cause element damage? We talked about chemistry, heavy solvents, inadequate flushing, those kinds of things. Talked about elevated pH, so I won't spend a lot of time there. Elevated pressures, probably haven't talked to that one as much as we should, but if our pressure drop gets way too high, it can cause some severe damage that then we're having to deal with later on. Elevated temperatures, that doesn't happen often, but it can on occasion. Anti-foaming, I think, we've talked about this before. Again, can't have those in our systems. They'll clog up the pores, silicone-based ones, of course. We also, everyone knows about using oxidizers on ROs and NFs. We probably don't talk about silica as much as we should. So poor water quality in our rinses can really cause irreparable damage on those elements. And Mark talked earlier about fats and particles, cheese fines, those kinds of things. If they get into elements, it can be very, very hard to remove. We've got to do some special washes and hope we can get those out of there. So talk about pressure drop. I think Glenn has discussed in really good detail about pressure drop and the importance of having a significant pressure drop in order to get CIP, good cross flow. But what isn't covered is if our pressure drop gets too high. That's why it's important to all of our manufacturers of elements will have their limitations, ranges of which they like to operate those elements to ensure good cross flow. But if we get too high or it gets outside of those ranges, it could cause some serious membrane damage. And here are some examples of what can happen if the pressure drop gets too high. So you can see there on the left-hand side where that outer wrap has pushed its way over the ATD. There in the center, you can see the Vexar migration. You can see that protruding out the end. And then the picture on the right shows some telescoping. You can kind of see how the membrane is starting to push its way out. All signs of too high pressure drop. Here's another example. You can see where the ATD has actually crushed the edge of the element. So you won't get the flow that you need across that element because the ends are all plugged off. And then the picture on the right shows that pop canning effect where you get where that element is again crushed. What can happen there when you get those kinds of damage on the element? It can impact the flow across that element. So you'll end up with dead spots in there where water product will not hit and will not get even flow. So you'll end up with definitely growth in that area where the CIP solution isn't able to get it clean. So this last one here, you can see the smiley faces there. Essentially, that element has come and it's starting to show channeling. A couple different causes. Pressure could definitely be an impactor there. And sometimes it could be a manufacturer's defect where they don't necessarily get that outer wrap as tight as it needs to be. So if you get that, what you'll end up doing is having high flows through those wider areas. So if you've got higher flow through there, that's going to indicate that you'll have less flow through other parts of the element. So therefore, you won't get the full effect, the full impact of that surface area for operation. And of course, then you won't clean it either. So can't have that.
Membrane autopsy. I know we've touched on kind of what it is. usually it's going to be the result of having an issue with the membrane, but often people who are proactive are going to want to do a membrane autopsy every time that they switch out membranes, just to see, is there anything that they're not getting off? And is there any type of damage that's indicative that their programming or their hydraulics are causing damage to the membranes faster than normal? So here we've got a picture of a membrane getting scraped. So if this is a membrane that has been fouled, a lot of times one of the diagnostic efforts that we'll do is we'll go ahead and take some of that soil off, test it in a couple of solutions like that former slide with the protein was showing, in order to see what dissolves it. And again, let me just repeat, this is going to be the fastest way to get information on what the foulant is and simultaneously come up with a solution based on what removes it the fastest. So this is something you can totally do in the field if they're taking out membranes. This is stuff that we'd love to do and partner with you. And it's often a lot faster than shipping samples to the lab and figuring out the logistics of getting that report to the customer and turning that into a practical solution. One of the things that we're going to be looking for is chemical damage. We've talked a little bit about the different chemistries that can cause damage, excessively high pHs, oxidizers, solvents, and generally this is going to be seen either as, in the extreme case, these cracks, but most commonly simply a membrane that cracks easily. So a membrane that doesn't have much flexibility when you pull it out, cut open, and start bending it. You'll either see this as cracks immediately or over time. I mean, there's actually a test that's been developed by several manufacturers, I think, that they use that it essentially determines the amount of folds that you can give a piece of membrane before it starts permeating a dye. Now, blistering, on the other hand, doesn't necessarily indicate chemical, as is sort of been widely thought. It's actually the result of the pressure on the feed side of the membrane pushing either polyvalent salt ions or in the wider pore membranes like your MFs and US, actually pieces of protein. And once they get in there, if they're near the glue line, they can't get out, and they act as an osmogen, so they pull water to them. And as they do this, they can just be water, which is not a huge concern from an inspection perspective, but the problem comes when that bubble increases and actually compromises the integrity of the membrane, and it starts sucking feed matter into there, and you start actually having essentially pus in your blisters, but it's just feed solution and the proteins involved. So a lot of companies have invested in blister-free membranes. However, you might still see this in the field, and this can be sort of a suggestion that their process needs blister-free membranes or some other more creative solution. So if the problem becomes big enough that we're sending stuff to the lab, we are going to probably want to look at some of the membrane surface to look at foulants, etc. But another thing that we can do is sort of the large-scale version of that practical soil test, which is putting the membrane in our test unit and running a couple of washes on it. And this is usually a secondary step after we think that we have an idea of what the foulant is, but it's a follow-on that we utilize to sort of verify that this is the wash that's going to solve the problem on the major system by scaling it up. We also have a flat sheet tester, and this probably works a little bit easier if we're sending in parts of a membrane that's been cut open, isn't in its full integrity, or just probably easier to ship a couple of sheets of flat sheet instead of the entire membrane. So there are super advanced, sexy looking analytical methods that might tell us a few additional details if we haven't solved it from this point. So we can send out material for a scanning electron microscope to look at. Here's some example imagery of the difference between a crushed, heavily soiled membrane and a clean membrane surface. So these are some pictures that we can see. Just remember that crushing is actually going to be a symptom that is going to occur to all membranes over time. So it's just the compaction of being under pressure. The polymers are not going to last forever in their pristine state. So this can tell us some things, especially if it's a brand new membrane that's exhibiting that type of crushing. But often this is not going to be a very definitive test. What the SEM, scanning electron microscope, can also tell us, though, is sort of the composition of that sample. So when the electrons are hitting your sample surface, some of them are going to reflect and give you the image. Some of them are also going to cause the molecules to release X-rays. And the X-rays are going to be specific in frequency to what that atom is that it's made up of. So as you can see here, we've got a virgin membrane compared to a soiled one. And by looking at what that dispersive X-ray scattering is and how it's different, we can sort of see what might compose the foulant in that dirty membrane based on what's there in the second one that's not there in the first. So a similar method that doesn't necessarily require such advanced techniques as FTIR, and this is going to use your infrared band wavelengths. This is going to be basically using, your low frequency levels of light, which is going to tell us something not necessarily based on the atoms, but on the bond types and their structure that make up the molecules that might be in the foulant. And again, this is going to be comparison between the membrane that hasn't been used, which we'll have to get from the membrane manufacturer, and the one that is probably fouled. And this just goes again to show you that the logistics in performing a lab analysis can be very useful if we can't figure out what it is in the field, but it will take some time and a lot of effort to put all the logistical pieces together. And it might be a lot simpler if you're just starting out with your problem to perform those soil tests in the field. And I think if you guys don't know on Tetrix, there is a soil analysis kit that Dylan in the lab put together, and it's got some pretty detailed instructions, and you could use that if you are pulling soil samples or a membrane out of a unit to get you a more rapid and practical solution to a fouling problem. But if it needs to be kicked up the chain, we do have the horsepower to find more complicated issues and figure out the solutions.